Hello, I'm Joe French, coming to you from my classroom in Mount Pleasant, Utah, and this is topic 2.6, derivative rules, constant, sum, difference, and constant multiple, and we'll go over some examples. So when we're taking derivatives of expressions, our expressions can have multiple terms, and we want to look at how those multiple terms might affect how we take the derivative. Fortunately, in these cases, the algebra we would normally think of applying does apply. First of all, let's talk about the constant rule. The derivative of a constant equals 0. Why is that true? Think about it for a bit. All right, so what does the graph of y equals a constant look like? Y equals 4. Well, that's just a nice horizontal line at y equals 4. What's the slope of this line? What is the instantaneous rate of change of this line? Well, it's not changing. It's not rising and it's not falling. So our rate of change, our derivative, is 0. The sum rule says that when we have two functions being added together, we can take their derivatives separately and add those derivatives together to get an answer. Very nice. It makes sense. Each of these derivatives is independent of each other, and when we take these derivatives of these functions, their derivatives are added together. The same thing works when we are subtracting, the difference rule. Derivative of the difference of two functions is the difference of their derivatives. The constant multiple rule says that when we have a coefficient being applied to a function, the derivative also includes that coefficient as part of the answer. So if I have the function 4x cubed, if I want the derivative of this, I can take the derivative of x cubed, which would be 3x squared, and that just gets multiplied by my coefficient. The coefficient just carries through. It doesn't get its own separate derivative process. It's included and carries through on the derivatives that we take. So let's look at some examples. Let f and g be differentiable functions such that f prime of 1 equals 2 and g prime of 1 equals negative 3. H of x is this function 4f of x minus 3g of x plus 2x cubed minus 6. So if we look at what's going on here, we are looking at the difference and sum of several terms, which is fine. That just means we can evaluate the derivatives of each term independently and then combine them with either sums or differences. And then some of our functions have coefficients, a 4 and a 3 and a 2. And down here at the end, we have a constant term. So we get to apply all the different rules that we've just looked at, all the ones that seem to make sense. So first, let's find h prime of x, and then we'll find h prime of 1. So h prime of x, this first term, 4f of x, the coefficient remains, and then we just have that times the derivative of f. The same thing here, we get to subtract, the coefficient remains, and then the derivative of g. Now the derivative of 2x cubed, we bring down the coefficient, or bring down the exponent and multiply it times the coefficient. So the 3 times the 2 gives me a 6x, and then subtract 1 from the original exponent, leaving me with x squared. Then the derivative of our constant, negative 6, is just 0, plus 0. But we don't usually just write that, so we'll leave it off. Now to find h prime of 1, that's going to be 4 times the derivative of f at 1, minus 3 times the derivative of g at 1, plus 6, and here we plug in the 1 for x and square it. and we replace f prime of 1 and g prime of 1 with the values they gave us. F prime of 1 was 2, so 4 times 2 minus 3, and g prime of 1 was negative 3, plus 6 times 1 squared, which is just 6. So that gives me 8 plus 9, the two negatives, plus 6, which turns out to be 23. Here's another example, just a straight power polynomial consisting of 3 terms that are power functions or constants. So to find f prime of negative 3, which is what they're asking us to do, I take my derivative, f prime of x, using my power rule and my constant multiple rule. I get 12x squared for the first term, minus 6. The derivative of 6x will be 6, the slope of a line y equals 6x, and then plus 0, because the derivative of a constant is 0. Then I plug in negative 3. So that would be 12 times negative 3 squared. Negative 3 squared is 9. And 12 times 9 is 108 minus 6. So my answer for f prime of negative 3 should be 102. That means my rate of change when x is negative 3 is a positive 102. Wow. Okay, let's look at one more example. Here I have graphs of f and g. And h of x is the function f of x minus g of x. So to find h prime of x, well, using our rules, h prime of x, since h of x is defined as the difference of f and g, the derivative will be the difference of the derivatives of f and g. Now, they haven't given us the equations, but they have told us that f and g are linear functions. Well, linear functions would mean that their derivatives are the same as the slopes of these lines. So we need to find the slopes of f and the slopes of g. So f is my red graph here, and I can see that as x goes up by 1, my y values increase by 2. So my f prime is going to be 2 over 1, or 2. Now g, I can see that as x increases by 2, in that same distance, my y values fell by 1. So g prime is going to be negative 1 over 2, which means that f prime of x minus g prime of x will give me 2.5, or 5 halves. Whoops, 5 halves. Mistake. Watch out for those negatives. And that's our last example for this topic.